Okay, in this video, we are going to approximate the area under the sine function on the interval 0 to pi. Now, this is a preview of what we're going to be doing later in the semester when we start integral calculus and we address the area problem, how to find the area under a curve, or the area bounded between a curve and the x-axis. Now, we're going to start with an approximation, and then we'll use limits to actually make that approximation exact. And the way we do that is by increasing the number of rectangles. So you'll see in this problem we have 3 rectangles in part 1 and 5 rectangles in part 2. All right, so let's just do part 1 because part 1 and 2 are basically the same. So we've taken the interval 0 to pi and it's partitioned into 4 equal subintervals. So this value right here would be pi over 4, and this value right here would be 3 pi over 4. All right, so use rectangles in each graph to approximate the area of the region bounded by the sine of x. So there's the sine of x is here on the interval 0 to pi. The line y equals 0, which is here, x equals 0, which is here, and x equals pi, which is here. So we're looking for an approximation of this blue shaded area, and we're going to use rectangles for that. So you can see with these rectangles, it may not look like a good approximation, but we've got some area under the graph. Basically, let's use red. So we have this area that's not going to be part of our estimate, and this area that's not going to be part of our estimate. But we have an overestimate here and an overestimate here. So these sort of will not exactly cancel out, but they'll come close to canceling each other out. So for the approximation, it's the total area should be equal to the area of each of these 3 rectangles added up. So we could say area 1 plus area 2 plus area 3. And in each one of these areas, it's a rectangle. So the area of a rectangle is base times height or length times width. So this first rectangle, say, looks about like that. The next one is a little bit bigger. Looks like that, and the third rectangle looks like that. So since we've taken the interval interval 0 to pi and cut it up into 4 subintervals, each one of those subintervals has a width of pi over 4. So this will be pi over 4, this will be pi over 4, and this will be pi over 4. It looks like the first rectangle and the third rectangle are identical copies of each other, so we could use that symmetry to simplify the calculations. Now, the first rectangle, the height is the y value when x is equal to pi over 4. So the height of the first rectangle should be the sine of pi over 4, which is the square root of 2 over 2. Now the height of the second rectangle here is the y value when x is pi over 2. So the sine of pi over 2 is equal to 1. And the third rectangle, the sine of 3 pi over 4 is the same as the sine of pi over 4, of course, so they're symmetric. So that's again root 2 over 2. So the total area should be, say area should be base times height. So we have pi over 4 times root 2 over 2 plus pi over 4 times the height, which is 1, plus another pi over 4 times root 2 over 2. All right, so let's simplify this before we pop it into the calculator. So we have root 2 times pi over 8 plus pi over 4 plus another root 2 pi over 8, and this first and third term, those are like terms, so let's combine those two. So that should be root 2 pi, well, 2 root 2 pi over 8, or root 2 pi over 4. All right, and so that's it. That's the exact area of those 3 rectangles, or that's our approximation. But in the directions, we're saying round to 3 decimal places. All right, so we're going to have to pop this into the calculator, and I have Desmos ready. Of course, Desmos is the calculator I'm always recommending we use. All right, so we're going to need to, oh yeah, that fits. So on Desmos, the square root is right here. So we have square root of 2 times pi. Okay, and we have to divide that by 4. And to that we will add pi over 4. Okay, so there's our approximation. We'll round this to 3 decimal places. So it looks like an area of about 1.896 square units. And that does it for our answer to this problem. So this is our exact area of the 3 rectangles, and this is our approximation. Okay, and so what we're going to do later when we address the area problem in terms of finding, so what we want to do eventually, is, if this is the sine function, sine of x, and this is pi. What we want to do eventually is find the exact area bounded between the x-axis and the sine function. And again, like I said, to do that, we'll take this same approach with rectangles, but as you see in part 1, we have 3 rectangles. In part 2, we have 5 rectangles. We could use 10 or 100 or 1,000. So as the number of rectangles gets larger and larger, this error here, so that's an underestimate, and this is an overestimate here. So the more rectangles we use, the less error there is. Okay, that does it for this one.